What if you take Biv out of it? What does it look like? Roig. What do sunsets look like? Roig. Yeah? That's because we've taken out the Biv, right? When we're here, the sun is here. When it's sunset, we're standing here looking at the sun through all this atmosphere. All the blue's been removed from it. Yeah? So now you can answer that question. I don't know if it takes, tell me why the sky is blue. Yeah? Now you know. Yeah?
So would it make more sense that why isn't the sky like purple then? Because violet's a small wave.
Because I don't know. I guess because if you average all of these, you get blue, maybe. I don't know. Yeah. You can't see the violet as well, but Mars's sky looks red, I think, because the particles are bigger in the sky. I mean,
You got more Roig?
yeah, more Roig. Ah! This is actually the little mites that live in your the follicles of your eyelashes.
What?
Just kidding. Okay, that's just an ant. But this is a scanning electron microscope. Okay, a scanning electron microscope, and this makes the the fancy images here. This is the yeah. The color on here is false color. It might be that it is actually a different compound. They can do that. They could have just colorized it too. And there's lots of other very cool pictures. Yeah. And then the final thing here is the Rayleigh criterion. Okay, is calculating the resolving power of like a telescope or a microscope. Okay, so I think a couple days ago when we talked about the interference patterns, right? I think I set the laser up there, and I shone it on a pair of slits, and the pair of slits made an interference pattern, right? But the story I didn't tell you at that time because maybe it was too confusing was that it actually works with a single slit, right? If you go off to the edge here, right, the difference between the edges and the center at this angle here is actually a half a wavelength, so that causes destructive interference. And then at a greater angle, if you angle it over a little more, right, now you've got like a full wavelength difference, and then you can get the same thing, right? So you get an interference pattern, and it's not as bright. There's a bright spot in the middle, dark spot, bright spot, dark spot. The middle, if it's a single slit, is definitely way more bright than it is relative to the other ones than it is with double slit patterns, right? So I already showed you the double slit pattern. And so the Rayleigh criterion is if you're looking up at the night sky and you have two stars and you want to see, if you want to resolve them, this is a criterion to say whether you resolve them or not. And it's arbitrary, but IB always manages to put at least one question on every single one of their tests about the Rayleigh criterion. It's every time. It's like, did they teach this obscure thing? Well, here it is. Okay? So the notion of whether they're resolved, okay, is this. Here is, by the way, a picture of what it looks like. So here is the intensity. There's the central bright spot. Do you see the bright spot? Right? And then if you see this, here's a dark spot, bright ring, dark ring, bright ring. Do you see those rings around there? So if you take the world's best telescope and you point it at a star and zoom way in on it, in fact, people who buy telescopes do this test to see if they get this perfect diffraction pattern, right? A good telescope, perfectly aligned and whatever they do to it, right? All of those adjustments, if it's perfectly tuned up, then all these circles are nice and concentric and it looks like that. That's what they look for, right? So basically there's this limit. You can't zoom in infinitely on a star and even see it. Most stars are just every star except our sun is just a point in the sky, right? And this is what happens to the light. You eventually get an interference pattern like that, right? Now here are two stars that are close together, right? And the Rayleigh criterion states that two things are resolved when the center spot of one falls on the first dark ring of the second one. Yeah? The center spot of one falls on the first dark ring of the second one, right? Do you see that that's happening, right? So this star here is falling right on that first dark ring. Are they actually separated in the telescope? No, but this is what they say. They say, okay, I know there's two stars there, not one, because I can see that, right? Is that reasonable? Right? So this is the Rayleigh criterion, and it's like we're looking at some other objects out there. So let's draw a picture of what we're talking about, right? Here's a telescope. Let's draw a nice telescope here. Okay, we've got the eyepiece here. We're looking in the eyepiece. Right? Out here there's a couple stars. And we're trying to tell whether we can resolve that, right? And this is the angle that we can resolve, right? And then this here is the aperture of the telescope. This is the B, right? Is this distance here, the aperture, the diameter, right? And then we also talk about the wavelength of light we're using. Lambda is the wavelength. Right? Now, the formula is that the angle is 1.22 times the wavelength over B, right? And the 1.22 is just this arbitrary thing. They're just shifting it over so that they're putting the bright spot on top of the dark spot. Yeah?
What exactly do you mean when you say resolve?
You can tell there's two.
Oh.
Yeah. How's that? Yeah. Okay. You can tell there's two stars there, right? It's good to get some resolution to that question, right? Be on the same wavelength, right? I mean, there was an opening there for some confusion. Okay, anyway. Yeah, anyway, that's the best picture here. So let's hit the right arrow and see if there's a... Oh, look at that. Okay. Here's a problem from last year's IB test, right? All this cryptic stuff here, I believe that means 2010, May of 2010 is my guess, right? Okay. And this is time zone 1. They have like different ones for different time zones, right? Okay. A space shuttle orbits at a height of 300 kilometers above the surface of the Earth. It carries two panels separated by a distance of 24 meters. So let's make these guys 24 meters apart, right? And then it's a distance of 300 kilometers, right? So this is 300 E3 meters, yeah, away from the telescope, right? The panels reflect light of a wavelength of 500 nanometers, so that's 500 nanometers times 10 to the minus 9 meters, right? Okay. And the observer views the panels with a telescope of an aperture of 85 millimeters. Well, good golly. Too many metric things, right? So 85, that's 8.5 centimeters, right? So that's like a small telescope, right? So I'm going to say that that's 8.85 E minus 3 meters. I know that's not proper scientific notation, but it's correct. That number is correct, right? Okay. And then it says, describe what is meant by the Rayleigh criterion. So here you would get 2 marks for saying that the Rayleigh criterion is a criterion for determining whether two objects can be discerned from one another from a distance. It depends on the wavelength of light, the aperture of the telescope, and an arbitrary number. And you could just write the thing down there. And I think that was 2 marks, right? And then it says, determine whether the images of the panels formed by the telescope will be resolved. Well, it's resolved if this angle is bigger than this angle. Yeah? This is the smallest angle you can resolve, right? This is the smallest you can, right? So let's figure out these 2 angles. Let's just figure it out, right? So this angle is 1.22 times 500 times 10 to the minus 9th meters divided by 85 times 10 to the minus 3rd meters, right? So the smallest we can actually resolve is 1.22 times 500 E minus 9 divided by 85 E minus 3. That's pretty small. That's 7.18, I'll say, times 10 to the minus 6 meters. Oops, radians. Meters divided by meters, right? How big is this angle? How do you figure out that angle? Do we know how? Is it really hard to do? What is it? I never knew that either. I was like, oh, is that how you do it? Isn't it just theta is just 24 divided by this, right? Theta is like S over R or something like that, right? Where S is the arc length. And then you're saying, gee, that's not an arc. Well, it's so far away that, it's the curved path between them at that radius is the same length.